Hello everyone. In this session, we are going to see about a topic called B trees. In the last session, we have seen about an A-will trees, which is an advancement of an binary tree. Once again, the B trees is just an advancement of an A-will trees. So whereas here in the B trees, what is the advantage of having in B trees? So here it is a very much powerful DSA topic. So where we can store the data in very much efficient way. So always in the B trees, it provides balanced tree structure. So here, unless a binary tree, each node can have maximum of two number of children. But here we don't have any restrictions like that. We can have multiple children for a node. So it is very much efficient storage. That's the main advantage. So we'll go into the topic and then we'll perform searching, insertion and deletion. And then we will discuss about the advantage of a B trees. So what's a B trees? It's an M by tree where each node is allowed to have maximum of M children. In binary tree, always each node can have maximum of 2. But here the difference is each node can have maximum of M. So what's advantage? So here I can store a number of datas under a single node will be very much larger. So for the searching of data will be very much easier compared to binary search tree. The order is M. Always we will call the order is M. And then the number of keys. The number of keys is nothing but is M minus 1. In each non-leaf node is going to be M minus 1. And then the non-leaf node except the root can at least maximum of m by 2 children, which is upscaling. So now we will see all these points in the diagram by means of like this. So now here you can see it's an m by tree. M by tree means what? So it's an order of 3. So 1, 2, 3. So the order is 3. Order is 3. So that means that B tree of order 3. Here you can see B tree of order 4. That means that a node can have maximum of M. 1, 2, 3, 4. What's a M? M is nothing but it's a pointer. It is a pointer. So whichever less than 18, we have it on the left node. And whichever is between the 18 to 45, we have in the center node. And whichever more than 45 will be having on the third pointer. That's a meaning of M way B trees. So first pointer is having less than 18, second pointer is having the between 18 to 45, and third pointer is having more than 45. You can see it over here. Whichever is 18, lesser than 18, it comes in the left pointer. So 9 and 11. So once again, in the 9, the leaf node also, we are having a 3 order, order of 3. Whichever having the value of lesser than 9, we'll be having left pointer. Between 9 and 11, we'll be having in the center pointer, and more than 11 will be having on the right pointer. Likewise, between 18 to 45, 27, 36, 29, and 30. More than 45, 54, 63, 72, and 81. So this is the B tree of order 3. And then this is a B tree of order 4. A maximum of 4 pointers can be there in a leaf node and minimum of 2. And then here it can have an m minus 1 keys. What's the m? M is nothing but order. So order is 3 means and each node can have maximum of m minus 1 keys, 2 keys. So here 2, 1845. Here 9 and 11, 2. 27, 36, 2 keys, 2 data can be there in each node. Whereas here order 4. That means that m minus 1, 4 minus 1, 3. So 3 data can be there in a single node maximum. So 54, 59, 61. Yeah, 3 data are there. Here 2, here 1. Minimum of 1 and maximum of 3. So this is the B tree of order 3 and this is the B tree of order 4. So how do you search a data? For example, if you are searching a data for 72 in this tree, so then what do you do? At first, we'll go and find the pointer, which pointer should be there. So if it's more than 18 and it's lesser than 45, I'll go in between the center pointer. Since 72 is more than 45, I'll go it on the right subtree. So then here I will find it's more than 63. So I'll go it on the right subtree. Then I will find the data over here, 72. This is how the searching operation will perform in the B trees. So how do we perform the insertion? So now straight away we'll show it by example. This is a B tree of order 5. So order 5 means what? There will be 5 pointers will be there. Lesser than 21, between 21 to 27, 27 to 36, 36 to 42, and more than 42. There are 5 pointers are there, maximum, and minimum can be a 2. So how much data can be stored in a single node? So m minus 1 keys, m minus 1 data can be stored in a single node. So 5 minus 1, there are 4 data can be stored, 27, 21, 27, 36, and 42. 4 data can be stored in a single node. So now we will try to insert a data called 8, 9, 39, and 4 into it one by one. So at first we will try to insert a data called 8. So insert 8. So where do you insert? This is a root node. In the root node, where do you insert 8? It will be on the left subtree, because whichever value is lesser than the 18 can be stored in the left subtree. So it comes over here. So in the left subtree, we are having 1, 2, 3. There are 3 pointers are there, but we are having an order of 5. So when we are having an order of 5, so here we are having only 3 pointers. So still we can add one more pointer over the left subtree. So we have inserted a data between an 7 and 11. We have inserted a data. So now 1, 2, 3, 4 pointers are there. It is fine. Now we will insert a 9 over here. Once again 9, which is lesser than the 18, it comes to the left subtree. Once again, we are doing for order 5. Order 5 means what? There are 5 pointers can be there. But in the left subtree, we are having only 4 pointers. So 7, 8. So 9 is inserted over here. 9 is inserted over here. So it is that this node is full. This node is full now. So now we will insert here 39. So where do you insert a 39 over here? Between 18 to 45. So between 18 to 45, so here we can see, uh, here we can see uh, between 36 to 36 and 42, we can insert a data. But here this node is already full. 1, 2, 3, 4, 5. There are 5 pointers are there. So this node is already full. So we can't insert a data over there. So now what do I do? Above the node, here I have only 4 pointers. So now I can break this node here. I can add a data over here. So now what happens over here? I will insert a 39. So now this node can be broken. This node can be broken. So 21 and 27 becomes separate node, and then 36 goes to the root node. 36 goes to the root node, and then 39 comes to the leaf node over here. Okay, so 36 goes to the root node. Between 18 to 45, 36 goes over there, and then 39 will be inserted over here. 39 and 42. This is how insertion can be performed inside a B tree. Now, next data is 4. Insert a 4. To where do we insert a 4 over here? I should come to the left subtree. Left subtree is already full. And then root node also already full. So now what I can do it over here? I can break this root node. Okay. So now what happens over here? I need to insert a 4. So now here I will take the 36 to the root node, and then whichever less than 36 is comes to the left subtree, and then from here I have taken a I have broken this node. 8 comes to the above node, 8 and 18, and then 4 is inserted over here. 4 is inserted over here. So since I have broken this, I have taken this 8 to the root node, 8 and 18. So whichever is lesser than 8 will come to the left subtree, whichever between 8 and 18 will comes to the center subtree, and whichever more than 18 comes to the right subtree. So this is how an insertion can be performed in the B trees. And next one is deletion. So deletion is we can perform by various ways. So for example, If I want to delete the 93 in this one, so then what I can do it over here? Simple. 90, 93, 101. It's a order 5. But there are 1, 2, 3, 4. Only 4 pointers are there. So 93 is simply deleted. So 93 is simply deleted over here. A simple step. And delete 201. So where's 201 here? 201 is here. So since 201 is in the root node, and then here 1, 2, 3, 4 data are there, 24, 243, 56, 33, 333, 450. So now the least node, okay, after 201, 243 is there, right? I will take it to the root side. I will take it to the root side and then delete 180. Where is 180? It is 180 over here. So now what happens over here? Between 117 and 243, there is only 151 and 180. If I delete 180, there will be 151 is only one data. And then whereas here I have 3 data are there. So which is very much imbalance. It is 1 and 3 over here. So I can take 243 to the downside and 256 to the upside. So 256 comes over here and 243 comes to the downside to maintain the balancing. By doing so, the searching of data will be very much easier for us. And then delete 72. So delete 72 means what happens over here? Here I can delete it. 72 can be deleted. By doing so, what happens over here? I can take the 36, 45, 63 and 79 as a single node. As a single node. So now I'll combine this 81, 108, 117, 256 into a single node. So the combination can be performed by doing it. So what happens over here? We can maintain the balance and then we can maintain the efficiency of searching data will be maintained throughout the B trees. So what's the advantage of an B trees? So the advantage of B trees is always balanced tree structure. So B trees are always balanced. So it's a fewer discusses. It is specifically each node can hold multiple keys. It reduces the height of the tree. So by doing it so, we can accommodate large data sets into the B trees. And then each node can have more than 2 children. Unlike binary trees can have only 2 children, each node can have more than 2 children. So it reduces the tree height, which improves performance, especially on the external memory. And then always we will store the data by means of sorted order. And then always we will use the memory in very much efficient way. So we can use the B trees. We can use it by means of dynamic, very much in dynamic range. So these are the advantages of an B trees. Thank you.